Hey everyone, welcome back. I am absolutely thrilled to have you here for today's explainer because we're going to be looking at the invisible mechanics of web security, literally decoding the architecture of trust itself by digging into JSON Web Tokens, or JWTs. If you've ever wondered how modern web apps just seamlessly remember who you are without nagging you for your password every single time you click a link, well, you're in exactly the right place. Let's get right into it.
So think about this everyday scenario, right? You log into a website, you close the tab, maybe you come back hours later and boom, you didn't log in again. But the server knows it's you. How? How on earth does every future request already know exactly who you are without you typing that password? It's not magic, I promise. And honestly, it's often not a traditional database either. The answer is this super compact, highly engineered piece of text called a JSON Web Token.
Okay, let's dive right into this. Here's our roadmap for the explainer. We'll start with the magic of stateless login. Look at the anatomy of a JWT. Explore the power of the signature. See how identity is verified. Flip over to the attacker's perspective. And wrap up with building secure systems.
All right, Section 1, the magic of stateless login, from heavy databases to lightweight tokens.
So back in the day with traditional sessions, every single time you clicked a link, the server had to rummage through this massive database or memory bank just to check its session records and confirm, yep, okay, they're logged in. It was a really heavy lookup process. But compare that to JSON Web Tokens. Think of a JWT like an unforgeable digital VIP pass. Instead of the server remembering you, the server just gives you the VIP pass. Your browser holds onto it, and you just sort of flash it at the door for every request. It's lightweight, it's stateless, and it literally eliminates that heavy database lookup entirely. A real game changer. Let's slow down a bit and move to Section 2, Anatomy of a JWT, dissecting the digital artifact. Now, what's really interesting about this is the structure. If you ever look at a raw JWT, it just looks like a massive string of gibberish separated by two periods, something like xxx.yyyy.zzz. But it perfectly breaks down into three very specific pieces. First up, the header, which has metadata like what algorithm is being used. Second, the payload, carrying the actual user data. And third, the signature, which is basically the cryptographic seal protecting the whole shebang. Let's zoom in on that middle section for a second, the payload. This is where the actual information about you lives. In JWT terminology, these pieces of data are called claims. A typical payload includes a subject, which is just a user ID, maybe a name, a role, and, absolutely crucial, an expiration timestamp. This is the authenticated info the server actually uses to know what you're allowed to do. But wait, we need a massive reality check here. It is a really dangerous myth that JWTs are encrypted and hide your secrets. Actually, scratch that. It's completely false. In reality, a standard JWT payload is merely base64 URL encoded. It is essentially plain text translated into an alphabet that travels well over the internet. So anyone, literally anyone who has the token can decode it and read the payload in seconds. Because of this, you must never, ever put passwords, private keys, or sensitive secrets in a JWT payload. Just don't do it. Okay, Section 3. The power of the signature, the holographic seal of authenticity. So if anyone can read the payload, how is it secure? Well, the secret sauce of the JWT is the digital signature. The server takes the header, takes the payload, and runs a really complex cryptographic computation over both of them. This creates a unique signature. And here is why this is pure genius. If a user tries to decode their token, change their role from user to, let's say, administrator, and send it back, the server will calculate a new signature. And guess what? That new signature won't match the one on the token. Modifying even a single tiny character in the payload instantly and completely invalidates the entire token. No way around it. And the cryptography gets even smarter. Modern systems often use public key cryptography, like the RS-256 algorithm. This is an asymmetric system. So the main authentication server uses a highly guarded private key to sign and issue the tokens. But all your distributed API microservices, they only need the public key to verify the tokens. They don't need the secret. This means you don't have to share your master secret across every single backend server. It's incredibly secure and scalable. Moving on to Section 4, verifying the identity, the invisible API handshake. So when your browser sends this token back to the API to say, hey, get my profile data, the server goes through a lightning-fast checklist, usually in just mere milliseconds. Step 1, extract the JWT from the authorization header. Step 2, decode the header and payload to see what it's dealing with. Step 3, and this is the absolutely critical step, verify the digital signature to ensure no tampering occurred. And Step 4, validate the specific claims like the expiration date. The server never ever trusts the payload until that signature is fully verified.
Now, there's this incredible engineering fact hidden in this process. When the server compares the signature it expects with the signature you sent, it uses what's called constant time comparison. If it used a normal string comparison, the process might fail slightly faster on the first wrong character than, say, the fifth wrong character. Believe it or not, hackers can actually measure those microscopic time differences to slowly guess a valid signature. Crazy, right? Constant time comparison ensures the check takes the exact same amount of time every single time, shutting down those timing attacks completely.
But even after the math checks out, the context still matters. The server rigorously interrogates the claims. It checks exp. Has the token expired? It checks is. Was this issued by our actual authentication server or some imposter? It checks odd. Is this VIP pass valid for this specific app, or was it meant for a totally different service? An NBF, or not before. Is it too early to even use this token? Only when all of this is validated does the server actually let you in. All right, Section 5, let's flip it around. The attacker's perspective, bypassing the math. So the crucial point here is that because of this incredibly strict cryptography, attackers are completely blocked from forging signatures, extending expiration times, or modifying their user role to suddenly become an admin. If they try any of that, the token is instantly useless. So instead of attacking the math, they pivot. They attack the implementation. They try to steal already valid tokens using cross-site scripting or XSS. They use browser malware. They hunt for poorly coded apps that store these tokens insecurely right on the client's device. It's a whole different battlefield. Which brings us to our final part, Section 6, building secure systems, protecting that VIP pass.
To actually defend against this stuff, one of the absolute most vital architectural takeaways for browser-based applications is storing JWTs in secure, HTTP-only cookies. See, because attackers rely so heavily on malicious JavaScript, like those XSS attacks we just mentioned, to steal tokens out of local storage, developers fight back using the HTTP-only flag. It is brilliant because it literally tells the browser, hey, do not let any JavaScript touch this cookie. It completely shields the VIP pass from client-side scripts, instantly neutralizing a massive category of attacks.
And this brilliantly illustrates the core philosophy of modern web security, summarized perfectly in this quote from our source material. Strong cryptography protects the token. Correct implementation protects the application. You can have the absolute most unbreakable RS-256 signature algorithm in the world, but if you just leave the tokens sitting out in the open for a malicious script to steal, well, your application is still compromised. It requires both. So, I'll leave you with this final provocative thought. The next time you open up your browser's developer tools and inspect the Network tab, take a look for the authorization header. If you see a long string starting with EJOY, you'll know exactly what you're looking at. It's a JSON Web Token. It's your digital VIP pass. And since you now know it's just base64 URL encoded, maybe you should decode your own payload and see exactly what secrets your token is carrying. Thanks so much for joining me on this explainer. Keep exploring, stay curious, and I'll catch you next time.